June 18, 1944, 0600 hours. The ancient hedgerows of Normandy, France, stood wrapped in morning mist so thick that visibility extended barely 20 meters in any direction. The air carried the smell of wet earth, crushed vegetation, and the ever-present odor of diesel fuel mixed with hot metal that characterized any concentration of armored vehicles. Staff Sergeant Curtis Morgan crouched beneath the belly of a Sherman tank, his hands black with grease up to the elbows, examining the final drive housing that had cracked for the third time that week. The fracture ran diagonally across the cast steel housing, a jagged line that spoke of metal fatigue and stress loads the component was never designed to withstand. Around him, spread across a muddy field that had been designated as the battalion maintenance area, the mechanized column of the 758th Tank Battalion sat silent and immobile in the morning mist. 23 tanks were disabled, not by enemy action, not by ammunition shortages or fuel problems, but by the grinding, relentless reality of European terrain that was destroying American armor through simple mechanical attrition. The battalion leadership believed they had 3 days, maybe 4, before they would be pulled from the line entirely and sent back to depot-level repair facilities that were already overwhelmed with similar cases from other units. They were catastrophically wrong about almost everything that was about to happen. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What Curtis Morgan was about to discover in those hedgerows, using nothing more than practical engineering intuition and materials that officially did not exist in any Army technical manual, would transform not just his battalion, but the tactical doctrine of armored warfare for the remainder of the European campaign, saving thousands of tanks and fundamentally altering the operational effectiveness of American armor in ways that senior commanders had thought impossible. Curtis Jonathan Morgan had enlisted in the United States Army in October 1942 from Detroit, Michigan, where he had worked for nearly 7 years at the massive River Rouge plant, Henry Ford's sprawling industrial complex that covered more than 2,000 acres and employed over 100,000 workers at its wartime peak. The River Rouge facility was a monument to vertical integration, producing everything from raw steel ingots to finished automobiles, converting iron ore and coal at one end into completed vehicles at the other. Morgan had started on the assembly line, but had quickly moved into the maintenance division, where his natural mechanical aptitude and his willingness to work through problems systematically had earned him a reputation as someone who could diagnose and fix equipment that other mechanics had given up on. He could hear the subtle differences in engine sounds that indicated bearing wear versus valve problems. He understood instinctively how stress distributed through mechanical systems and where failures were likely to occur. These were not skills learned from textbooks, but from years of hands-on experience, from countless hours spent with tools in hand, learning how metal behaved under different conditions. When Morgan had received his draft notice in September 1942, he had made a deliberate decision. Rather than waiting to be assigned wherever the Army decided to send him, he had voluntarily enlisted and requested assignment to an armored unit, believing that his extensive mechanical background would serve him well and might even keep him off the front lines in a direct combat role. The Army, desperate for technically skilled personnel to maintain the increasingly complex machinery of modern warfare, had been happy to accommodate his request. What Morgan had not fully understood at the time was that as a black man in the American military of 1942, his options were constrained by policies that the Army maintained despite the enormous demands of fighting a global war. He found himself assigned to the 758th Tank Battalion, one of several segregated armored units that the Army had reluctantly formed under pressure from civil rights organizations, particularly the National Association for the Advancement of Colored People, and in response to the simple mathematical reality that fighting a two-front war against major industrial powers required mobilizing every available resource, including black Americans, who had historically been excluded from combat roles or relegated to service positions. The battalion had been activated at Fort Hood, Texas, in January 1943, and had spent the next 18 months training intensively to maintain and operate the M4A1 Sherman medium tank, a 33-ton vehicle that represented the backbone of American armored forces. The Sherman tank itself was a machine that embodied American industrial philosophy. It was not the most heavily armed tank, with its 75mm main gun being outmatched by heavier weapons on opposing vehicles. It was not the most heavily armored, with frontal armor ranging from 51mm to 76mm depending on the specific variant, protection that was adequate against most weapons, but vulnerable to the latest anti-tank systems. What the Sherman had, what made it the foundation of American armored doctrine, was producibility and reliability. It was powered by a Continental R975 radial engine, a 9-cylinder air-cooled engine that had been adapted from aircraft use and produced 400 horsepower at 2,400 revolutions per minute. This engine had been chosen not because it was the best possible power plant, but because it was already in mass production and could be manufactured in quantities that more sophisticated alternatives could not match. The entire Sherman design philosophy prioritized ease of production, ease of maintenance, and tactical flexibility over individual vehicle superiority. American factories were producing Sherman tanks at a rate that astonished even the military planners who had ordered them. At peak production, which had been reached in late 1943 and early 1944, American industry was turning out 1,725 Sherman tanks per month, rolling off assembly lines in 11 different plants scattered across the United States. This represented not just a triumph of manufacturing, but a fundamental strategic advantage. The opposing forces, despite producing individually superior vehicles in many cases, could not begin to match these production numbers. Every tank they built required skilled labor that was increasingly scarce, precision components that were increasingly difficult to manufacture under wartime conditions, and specialized alloys that were increasingly impossible to obtain as supply lines collapsed. American tanks, by contrast, could be produced faster than they could be destroyed, creating a material advantage that translated directly into strategic superiority. Lieutenant James Colton, the battalion maintenance officer, stood watching Morgan work. Colton was from Philadelphia, Pennsylvania, a graduate of Howard University who had earned his commission through officer candidate school. He carried a clipboard thick with maintenance reports, each page documenting another mechanical failure that seemed to have no solution within standard Army procedures. "Morgan," Colton said, his voice tight with frustration, "that's the fourth final drive housing this week. We're burning through parts faster than supply can truck them forward. At this rate, we'll have more tanks deadlined than operational by the end of the month." Morgan slid out from beneath the tank, wiping his hands on a rag that was already saturated with oil. He was 27 years old, with the kind of lean build that came from years of physical labor. His face was thoughtful as he looked up at the lieutenant. "Sir, the problem isn't the parts themselves," Morgan said slowly, working through the problem as he spoke. "The housings are cracking because the entire drivetrain is taking shock loads it was never designed for. Every time we hit one of these hedgerows, the impact transfers straight through the transmission and into the final drives. The Germans built their tanks with that kind of punishment in mind. We didn't." Colton nodded grimly. He had read the after-action reports from other units. The German tanks, particularly their heavier models, seemed to handle the terrain with relative ease. But those reports also noted something else. The German forces were increasingly unable to replace their losses. Every tank destroyed or abandoned was one less tank in their inventory. The Americans, by contrast, could afford to lose tanks at a ratio that would bankrupt any other nation's armor force, but only if those tanks actually made it to combat rather than breaking down in transit. "The engineers are working on a solution," Colton said, but his tone suggested he didn't believe it would arrive in time. "Something about reinforcing the hull at the stress points. But that requires pulling tanks back to depot for modification." Morgan stood, looking at the line of disabled Shermans. Each represented not just a tactical asset lost, but hours of work, tons of spare parts, and the knowledge that somewhere infantry units were operating without the armored support they desperately needed. He thought about the River Rouge plant, about how problems got solved on the factory floor through improvisation and practical engineering, rather than waiting for the design team to issue new blueprints. "Sir," Morgan said carefully, What if we don't wait for the engineers? That evening, Morgan gathered a small team in the maintenance area. Corporal Jackson Hayes from Birmingham, Alabama, who had worked as a welder before the war. Private First Class Robert Timmons from Chicago, Illinois, who had been a machinist at a tool and die shop, and Sergeant Leon Walker from Oakland, California, who had spent 6 years as an auto mechanic before being drafted. They were all members of the 758th, all black soldiers serving in a segregated unit, all intimately familiar with the reality that their solutions would need to work the first time because they would not get the benefit of the doubt if they failed. Morgan explained his thinking. The final drive housings were failing because they were designed to handle rotational stress, not impact stress. Every time a Sherman hit a hedgerow or dropped into a ditch, the shock traveled through the track, into the drive sprocket and directly into the housing. The metal was simply fatiguing under repeated impact. So we need to absorb the impact before it reaches the housing, Hayes said, following the logic. Something that can flex without breaking. Springs, Timmons suggested. If we could mount the entire assembly on springs, like a car suspension, it would cushion the impact. Morgan shook his head. Too complex. We'd need to redesign the entire mounting system, and we'd need parts we don't have. We need something simpler, something we can fabricate right here with what we've got. Walker, the oldest of the group at 34, was quiet for a moment. Then he spoke. What about wire coils? Like the kind they use for heavy-duty electrical systems. If we could wind thick wire into coils and mount them between the housing and the hull, they'd compress under impact and then spring back. It's not perfect, but it might absorb enough of the shock to keep the housings from cracking. The group considered this. It was crude, improvised, and absolutely not covered by any Army technical manual. It was also exactly the kind of practical solution that might actually work. "Where do we get the wire?" Colton asked. He had been listening from the shadows, interested despite his official responsibility to ensure all repairs followed proper procedure. "Telephone wire," Morgan said immediately. "The signal core has spools of it. It's steel core designed to take tension. If we can get enough of it, we can wind it into coils tight enough to provide real resistance." Colton was silent for a long moment. What they were proposing was technically a violation of regulations. Modifying military equipment without authorization was a court-martial offense. But Colton was also looking at a situation where by-the-book procedures meant watching his battalion's combat effectiveness drain away while they waited for solutions that might never arrive. "Do it," Colton said finally, "but you've got 72 hours. If it doesn't work, we go back to standard procedure and pray the depot can get us parts in time." The next morning, as the sun burned off the persistent Normandy mist and revealed another day of overcast skies threatening rain, Morgan and his carefully selected team began the process of scrounging the materials they would need for their experiment. In the military, official requisition procedures existed for everything, but those procedures moved at a pace measured in weeks or months, and Morgan had been given 72 hours. That meant operating in the unofficial economy that existed in every military formation, where favors were traded, stories were told, and materials somehow found their way to where they were needed most urgently. The Signal Corps detachment supporting the division maintained substantial stocks of field telephone wire, essential for maintaining communications in an environment where radio could be unreliable, and where the constant movement of units meant that telephone lines needed to be laid, repaired, and relayed on an almost daily basis. When Morgan first approached them, explaining that he needed several spools of their precious wire for an experimental tank repair, the Signal Corps sergeant, a man named Patrick O'Brien from Boston, Massachusetts, was understandably skeptical. Wire was currency in the Signal Corps world. It was the foundation of their ability to do their jobs, and they guarded their stocks carefully against the constant demands of other units, who always seemed to need wire for purposes that the Signal Corps considered frivolous. But Morgan had learned, during his months of service, that skepticism could often be overcome with honesty and specific detail. He didn't make vague promises or try to pull rank. Instead, he sat down with O'Brien and explained exactly what he was trying to do, drew diagrams showing how the wire coils would be positioned, and walked through the engineering logic that suggested this might actually work. He explained the final drive housing problem in terms that a communications technician could understand, relating it to the kind of stress that telephone cables experienced when strung between poles that swayed in the wind. The wire needed to absorb motion without transmitting full force to the connection points, exactly the same principle Morgan was trying to apply to the tank's drivetrain. O'Brien, impressed by the thoughtfulness of the approach and perhaps moved by the desperation he could see in Morgan's face, agreed to release 6 spools of wire from his stocks. Each spool contained approximately 1,000 meters of field telephone wire, a remarkable piece of engineering in its own right. The wire consisted of a steel core for strength, wrapped with copper for conductivity, and insulated with a rubber compound that could withstand moisture, temperature extremes, and the rough handling inevitable in military use. The steel core was what interested Morgan. That inner strength, combined with the flexibility provided by the copper wrapping and rubber insulation, created exactly the properties he needed. The ability to resist compression while still providing some give under load. The process of creating the wire coils was painstaking work that required precision and patience, qualities that Morgan possessed in abundance. They set up their workspace in a corner of the battalion maintenance area, clearing away the usual clutter of spare parts, empty oil drums, and discarded track links to create a clean area where they could work without contamination or distraction. Hayes, whose welding experience had taught him the importance of proper setup, insisted on this clean workspace. As he explained to the others, if they were going to do precision work, they needed a space that supported precision. For the mandrel, the cylindrical form around which they would wind the wire to create the coils, they used a section of steel pipe that Morgan had salvaged from a damaged fuel line. The pipe had an outside diameter of approximately 7 centimeters, which Morgan had calculated would create coils of the right size to fit within the available space between the final drive housing and the hull mounting points. The calculation had required Morgan to measure those spaces carefully, accounting for the fact that the coils would need to compress under load without bottoming out against either surface. Too large, and the coils wouldn't fit. Too small, and they wouldn't provide adequate cushioning. Hayes cut the pipe into sections roughly 15 centimeters long, creating multiple mandrels so that several coils could be wound simultaneously. He then welded short handles onto each mandrel, giving them something to grip while winding the wire. These mandrels became the foundation of their production process, simple tools that enabled them to create consistent coils with repeatable properties. The actual winding process required a combination of strength and fine motor control. They would secure one end of the telephone wire to the mandrel, then begin wrapping it around the pipe, keeping tension constant and spacing consistent. Each wrap needed to sit snugly against the previous wrap without overlapping or leaving gaps. Too loose and the coil would have inconsistent spring properties. Too tight, and the wire might damage itself during winding. They developed a rhythm with one person turning the mandrel while another fed the wire, maintaining just the right tension through the grip of their hands and the resistance they provided. Each coil required approximately 30 meters of wire and took about 45 minutes to wind properly when the team was working efficiently. The first coil took nearly 2 hours as they experimented with technique, discovering through trial and error how much tension to maintain, how tightly to wind, and how to finish the end securely so the coil wouldn't unravel. But by the 5th coil, they had developed a standardized procedure, and the time dropped to the target, 45 minutes. By the end of the first day, working through the morning, afternoon, and well into the evening, they had produced 24 coils, arranged in neat rows on a clean tarp where they could be inspected and tested. The goal was to create coils that were stiff enough to support the weight of the drive assembly, which Morgan estimated at roughly 200 kilograms for the entire final drive unit, but flexible enough to compress under the sudden impact loads that occurred when the tank hit a hedgerow. This required finding a balance point that couldn't be calculated theoretically with the tools and knowledge available to them. Instead, they tested each coil by placing it on a flat surface and carefully stacking weights on top, observing how much it compressed under different loads. They were looking for coils that would compress approximately 3 centimeters under the static weight of the drive assembly, but had reserve capacity to compress further under impact without reaching solid compression, where the wire coils pressed against each other and stopped absorbing energy. Hayes, with his welding experience and his background in fabricating structural supports, took charge of creating the mounting brackets. These brackets were critical because they had to serve multiple functions simultaneously. They needed to hold the wire coils in precise position between the final drive housing and the hull mounting points. They needed to be strong enough to resist the forces involved without bending or breaking. They needed to be designed so that they could be installed and removed with standard tools, because maintenance accessibility was crucial. And they needed to be light enough that adding them to every tank wouldn't significantly affect the vehicle's weight distribution or performance characteristics. Hayes worked with scrap steel plate that he had accumulated over weeks of maintenance work, pieces salvaged from damaged vehicles, cut-offs from fabrication projects, and odd-sized remnants that the supply system considered unusable. He had a talent for seeing potential in these scraps, for visualizing how a bent piece of armor plate could be cut and reformed into something useful. Using a cutting torch, he shaped the brackets, creating U-shaped channels that would cradle the wire coils. He drilled mounting holes with careful precision, ensuring they would align with existing bolt holes in the hull, so that installation wouldn't require any permanent modification to the tank itself. The brackets had to be reversible, had to allow the modification to be removed if it proved unsuccessful, or if higher headquarters ordered it discontinued. The welding work required particular care. Hayes used an arc welder, working with precise, controlled movements to create strong joints without introducing stress concentrations that might become failure points. He inspected each weld carefully, looking for signs of porosity, inclusions, or incomplete penetration that might compromise structural integrity. This was not decorative welding, but structural welding, where the quality of the work directly determined whether the brackets would hold up under combat conditions. Hayes had learned his trade in the shipyards of Birmingham, where sloppy welding could sink a ship and kill a crew. He brought that same exacting standard to these improvised tank brackets. By the evening of the second day, working straight through with minimal breaks for food and sleep, they had fabricated enough coils and brackets to modify one Sherman tank. This represented roughly 48 hours of nearly continuous work, with the team rotating through short rest periods while others kept the production going. They had consumed all 6 spools of telephone wire that O'Brien had provided, created 48 individual wire coils, and fabricated 8 mounting brackets, 4 for each side of the tank, each bracket positioned to support multiple coils. Morgan selected the tank for the initial modification with care. He chose a Sherman that had already suffered one cracked final drive housing, which had been repaired using conventional methods, removing the damaged housing, installing a replacement from depot stocks, and hoping the same thing wouldn't happen again. This tank represented the perfect test case. Its drivetrain had already been weakened by one failure. If the wire coil system could protect this already damaged vehicle, then it would certainly protect undamaged tanks. If it failed to protect this tank, then they would know immediately that the system wasn't robust enough for operational use. Installing the modification took 6 hours of concentrated, methodical work that tested both the precision of their preparation and their physical endurance. The task was complicated by the fact that they needed to work in the confined space beneath and around the tank, where every movement had to be deliberate and where there was no room for error. They began by jacking up one side of the tank, using the standard maintenance jacks that were part of the battalion's equipment, carefully positioning blocks to ensure stability, because working under a 33-ton vehicle that might shift or settle was a recipe for disaster. With the tank secured and elevated, they partially disassembled the track and suspension system on the right side, the side that had previously suffered the cracked housing. This required removing dozens of bolts, carefully cataloging each one because different locations used different bolt lengths and grades, and mistakes during reassembly could lead to failures that might prove catastrophic. Each track link weighed approximately 20 kilograms, and the assembled track for one side weighed well over a ton. They needed to support this weight carefully as they loosened the connections, using chain hoists and careful leverage to prevent sudden shifts that might injure someone or damage components. The final drive housing itself was accessible only after the suspension components were moved aside. Morgan examined it carefully, before beginning the installation, running his hands over the surface, feeling for any signs of stress or weakness that might indicate this tank wasn't suitable for testing. The previous crack had been professionally repaired at depot level, with the damaged housing replaced entirely, but Morgan wanted to verify that the replacement was properly installed, and that no additional damage had occurred to surrounding components. Satisfied with what he found, he moved to the next phase. Positioning the mounting brackets required extreme precision. Each bracket had to align with existing bolt holes in the hull structure, holes that had been drilled at the factory with tolerances measured in fractions of a millimeter. Hayes had done excellent work fabricating the brackets, but there was always some variance in hand fabrication, and they needed to verify that each bracket would mount properly before proceeding. Morgan and Timmons worked together, one holding the bracket in position while the other tried to thread bolts through the holes, checking alignment and making minor adjustments using files and careful bending where necessary. Once the brackets were properly positioned, they began installing the wire coils. Each coil needed to be compressed slightly to fit into the space between the bracket and the final drive housing, which required careful use of leverage and gradual, even pressure. Too much force applied too quickly might deform the coil or cause the wire to bite into itself, potentially creating weak points. Too little force and the coil wouldn't seat properly, leading to uneven load distribution that might cause the bracket to fail under stress. Morgan had devised a technique using wooden wedges and careful hammering, compressing each coil gradually while checking that it remained properly aligned and that the compression was even across the entire coil diameter. The process had to be repeated 8 times, once for each mounting point, and each installation took approximately 45 minutes of careful work. Walker, watching the process and understanding the principle involved, suggested a refinement. Rather than installing all the coils to the same compression, they could vary the compression slightly, making the coils closer to the center of impact slightly stiffer than those farther away. This would create a progressive spring rate, where initial impacts would be absorbed by the softer outer coils, and only severe impacts would compress all the coils, including the stiffer central ones. Morgan considered this idea carefully, recognized its merit, and incorporated it into the installation, adjusting the compression of each coil based on its position. With all the wire coils and brackets installed, they began the careful process of reassembling the track and suspension system. This was where errors could prove costly, where a bolt installed to the wrong torque specification or a component positioned incorrectly could lead to failure that might be attributed to the modification rather than to the reassembly error. Morgan insisted on double-checking every step, having one person perform each operation and another verify it before moving on. This slowed the process considerably, but ensured quality. The final bolt was torqued down at 1600 hours, 6 hours after they had begun the installation. Morgan lowered the tank back onto its suspension, checking for any unusual sounds or movements that might indicate a problem. He then performed a series of static tests, having the driver start the engine and engage the transmission with the tracks blocked, verifying that the drivetrain operated normally with the modification in place. Everything functioned as it should. The modification appeared mechanically sound, but the real test would come when they subjected it to the kind of punishment that had been destroying unmodified Shermans. Lieutenant Colton watched the entire installation process with a mixture of hope and apprehension that grew more intense as the day progressed. He had taken a calculated risk by authorizing this experiment, stepping outside the bounds of regulations that explicitly forbade unauthorized modifications to military equipment. His career as an officer, his reputation in the battalion, his future prospects, all hung on the outcome of the next few hours. If the modification failed catastrophically during testing, if the wire coils proved inadequate and the final drive housing cracked anyway, or worse, if the modification itself caused new problems that led to injury or equipment loss, Colton would be the officer who authorized an unsafe field modification. Courts-martial had been convened for less serious violations of regulations, but if it worked, if this improvised solution proved effective, he would be the officer who had solved a problem that was degrading American armor effectiveness across the entire theater, and that kind of achievement could define a career. "How will we know if it's working?" Colton asked, as Morgan torqued down the final bolt, his voice betraying the tension he was feeling. "We test it," Morgan said simply, his own voice calm despite the enormity of what they were about to attempt. "We take this tank over the worst terrain we can find and see if the housing survives. If the coils compress properly and the housing shows no signs of stress after 3 hours of maximum intensity operation, then we know the principle is sound. If it fails, we'll learn what went wrong and either fix it or acknowledge that this approach isn't viable." The test began early the following morning, June 20th, with conditions that were almost deliberately challenging. The morning fog was particularly thick, reducing visibility to perhaps 30 meters, and the ground was muddy from overnight rain, conditions that would make the terrain even more treacherous and increase the stress on the tank's drivetrain. Sergeant Marcus Williams from Atlanta, Georgia, one of the battalion's most experienced drivers who had been operating Shermans since the unit's activation, climbed into the driver's position of the modified tank. Williams was 29 years old, had worked as a truck driver before the war, and had that instinctive feel for machinery that separated competent operators from exceptional ones. He could sense through the controls when a vehicle was operating normally and when something was beginning to go wrong, often detecting problems before instruments registered any abnormality. Morgan rode in the assistant driver's position, a seat normally occupied by a crew member who operated the hull-mounted machine gun, but which for this test would allow Morgan to monitor the engine and drivetrain sounds directly, listening for any indication of problems. From this position, he could also easily dismount to perform the frequent inspections that would be crucial to evaluating the modification's performance. Colton observed from the turret, occupying the tank commander's position, where he would have the best overall view of the test and would make the tactical decisions about where to drive and what obstacles to challenge. They deliberately sought out the most punishing terrain they could find in the immediate area. The hedgerows of Normandy provided no shortage of challenging obstacles. Some hedgerows had been partially broken down by previous tank traffic, but remained substantial barriers. Others were pristine, untouched by military operations, presenting the full challenge that made them so effective as defensive terrain. Colton directed Williams toward a particularly dense section of bocage, about 2 kilometers from the maintenance area, a place where several tank platoons had attempted to operate during the previous week, and where multiple final drive housing failures had occurred. For 3 hours, Williams subjected the tank to punishment that would normally crack a final drive housing within the first hour of operation. He approached hedgerows at various speeds and angles, testing how the modification performed under different impact conditions. At lower speeds, around 15 kilometers per hour, the tank would climb the hedgerow embankment with a grinding, steady pressure, tracks chewing into earth and roots, engine laboring under load but not overloaded. These were the conditions that caused chronic fatigue failures, repeated moderate stress that accumulated over time. At higher speeds, 25 to 30 kilometers per hour, the tank would hit the hedgerow with tremendous impact, the entire vehicle shuddering from the collision, crew members bracing themselves against the shock. These were the conditions that caused acute failures, single violent impacts that could crack a housing in one blow. Williams dropped the Sherman into ditches at angles that made Colton wince, the tank tilting at extreme angles that tested the limits of its stability. Coming out of ditches was particularly punishing on the drivetrain, with one track often losing traction while the other carried full load, twisting the suspension and drive system with tremendous force. He rammed hedgerows head-on, letting the bow strike first with full weight behind it, then reversed and hit them at 45-degree angles, letting one track take the initial impact while the other track provided leverage. He executed sharp turns on uneven ground, conditions that twisted the suspension to its limits and created complex multidirectional stress patterns in the drivetrain. After each major maneuver or series of impacts, Morgan dismounted and performed a thorough inspection of the final drive housing and the modification. He would drop to his hands and knees in the mud, ignoring the discomfort and the filth, reaching up into the drive assembly to run his hands over the housing surface. He was feeling for the telltale signs of stress, heat buildup that would indicate friction or binding, vibration patterns that would suggest loose components or developing cracks, and the subtle changes in surface texture that could indicate metal deformation. He checked the mounting brackets with equal care, looking for any signs of bending or loosening, verifying that bolts remained tight and that welds showed no cracking. Most importantly, he examined the wire coils themselves. After particularly hard impacts, he could see that the coils had compressed, sometimes by as much as 4 or 5 centimeters, exactly as designed. But the critical question was whether they recovered fully after compression, returning to their original length and maintaining their spring properties. Using a measuring tape and careful observation, he verified that the coils were indeed recovering completely, showing no signs of permanent deformation or wire damage. The progressive spring rate that Walker had suggested was working beautifully. Lighter impacts compressed only the outer, softer coils, while harder impacts brought the stiffer inner coils into play, providing exactly the kind of graduated protection that would maximize the service life of both the coils and the housing. By noon, after 3 solid hours of systematic abuse, it was clear that something remarkable was happening. The final drive housing showed absolutely no signs of stress. There was no abnormal heat buildup, no unusual vibration patterns, no surface changes that would indicate developing problems. The wire coils were functioning exactly as intended, absorbing impact energy that would otherwise have been transmitted directly into the vulnerable cast steel housing and dissipating it through compression and recovery rather than allowing it to accumulate as fatigue damage. The modification was not just working. It was working better than Morgan had dared to hope. Colton, recognizing that they had something that could genuinely transform the battalion's operational effectiveness, immediately ordered the modification applied to every operational Sherman tank in the battalion. This was a significant commitment, requiring them to dedicate essentially all of their maintenance capacity to installing the wire coil system, temporarily setting aside routine maintenance and minor repairs in favor of this higher priority. But Colton had seen enough. The test had been conclusive. The modification worked, and every hour they delayed in implementing it across the fleet was an hour where tanks remained vulnerable to the final drive failures that were crippling their combat effectiveness. Morgan and his team, despite their exhaustion from the previous 72 hours of nearly continuous work, understood the urgency and threw themselves into the mass installation effort. They organized the work systematically, setting up multiple installation stations in the maintenance area, each staffed by mechanics who had been trained on the procedure. Morgan personally supervised the first installation at each station, ensuring that every mechanic understood not just the mechanical steps, but the reasoning behind them, the critical points where precision mattered most, and the inspection criteria that would determine whether an installation was acceptable or needed to be redone. They worked around the clock, mechanics rotating through shifts, with some teams installing coils and brackets, while others fabricated new coils to keep pace with demand. O'Brien, the Signal Corps sergeant who had provided the initial wire, proved invaluable, somehow obtaining additional spools when the initial stock ran out, pulling favors and making trades throughout the division's support network. Hayes ran the fabrication shop, producing mounting brackets with assembly line efficiency, each bracket identical to the last because he had perfected his technique to the point where he could work almost automatically. Timmons managed quality control, inspecting each completed installation, checking torque specifications, verifying coil compression, and signing off only when he was satisfied that the work met Morgan's exacting standards. Within 48 hours of the successful test, 21 tanks had been modified with the wire coil system. This represented essentially the battalion's entire operational fleet, minus only those tanks that were already deadlined for other reasons, or that were actively on mission and couldn't be pulled back for modification. The achievement was remarkable not just for its speed, but for its consistency. Each installation was performed to the same standard, each tank received the same protection, and each modification was documented so that mechanics in other units could replicate the work if needed. The real test came on June 24th, when the 758th received orders to support an infantry advance through particularly dense hedgerow country. The operation required the tanks to make repeated assaults on fortified positions, each assault involving multiple high-speed impacts with earthen embankments that would normally destroy final drives within hours. The modified Shermans performed flawlessly. Tank after tank crashed through hedgerows, dropped into ditches, and climbed steep embankments without suffering drivetrain failures. The mechanics who accompanied the advance reported that the wire coils were performing even better than the initial tests suggested, with some coils showing the ability to absorb hundreds of impact cycles without degradation. Word of the modification spread rapidly through the armored forces in Normandy. Maintenance officers from other battalions began visiting the 758th, observing the wire coil installation and requesting permission to replicate it in their own units. Within a week, the modification had been adopted by 3 other tank battalions. Within 2 weeks, it had reached division headquarters. Major General Harold Richardson, commanding the 4th Armored Division, personally visited the 758th to observe the modification. Richardson was a career armor officer who had spent the years before the war arguing for mechanized warfare doctrine. He understood that tactics were meaningless if the tanks couldn't reach the battlefield intact. Richardson watched as Morgan demonstrated the installation procedure, explaining the reasoning behind each step. The general asked technical questions, probing the limits of the modification. How much weight did it add? Did it affect ground clearance? Could it be installed in the field without specialized tools? Morgan answered each question with the confidence of someone who had not only designed the system, but had personally tested it under combat conditions. The wire coils added approximately 12 kilograms per side, negligible in a 33-ton vehicle. Ground clearance was unaffected because the coils were mounted within existing space. Installation required only standard mechanics tools and could be completed by a competent crew in 6 hours. "Sergeant Morgan," Richardson said when the demonstration concluded, "you've solved a problem that was costing us more tanks than enemy action in some sectors. I'm forwarding a recommendation that this modification be adopted as standard procedure theater-wide." What Richardson didn't say, but what everyone present understood, was that a black mechanic from a segregated unit had achieved what the Army's engineering corps had not: a practical, field-implementable solution to a critical mechanical problem. It was a moment that complicated the simple narratives both the Army and American society preferred to tell about race and capability. The modification that became known unofficially as the Morgan Coil was adopted across American armored forces in Europe over the following months. Engineering depots began producing prefabricated coil and bracket kits that could be installed during routine maintenance. The modification was refined, with later versions using purpose-made spring steel instead of telephone wire. But the fundamental principle remained the same: absorb impact stress before it reaches vulnerable components. The impact on tank availability was dramatic. Units equipped with the modification reported final drive housing failures, dropping by 73%. Tanks that would have been deadlined for days or weeks remained operational. The increased availability translated directly into tactical flexibility, allowing commanders to sustain operations that would previously have been impossible due to mechanical attrition. But there was another impact, one that couldn't be measured in maintenance reports or operational readiness statistics. The 758th Tank Battalion had demonstrated something that many in the Army's leadership had doubted: that black soldiers were capable not just of following procedures, but of innovation under pressure, of solving problems that defeated conventional approaches. Lieutenant Colton submitted Morgan for the Legion of Merit, the military's award for exceptionally meritorious conduct in the performance of outstanding services. The recommendation was endorsed by Richardson and forwarded up the chain of command. It disappeared into the bureaucracy and was never acted upon. Morgan would leave the Army in 1946 with the rank of Technical Sergeant, his service record noting his mechanical expertise, but making no mention of the modification that had saved hundreds of tanks and, by extension, thousands of lives. The 758th Tank Battalion continued to serve throughout the European campaign, participating in operations in France, Belgium, and Germany. They fought at the Battle of the Bulge in December 1944, where the reliability of their tanks proved crucial during the chaotic winter fighting. They were among the first American units to reach the Rhine River in March 1945. Throughout these operations, the wire coil modification remained standard equipment on their Shermans. Other units adopted it. Engineering teams studied it. Technical manuals were eventually updated to include it as an authorized field modification, but the name of the man who invented it gradually faded from official records, replaced by bureaucratic language about field-developed solutions to drivetrain stress. After the war, Morgan returned to Detroit. He went back to work in the automotive industry, applying his military experience to civilian production. He rarely spoke about his time in the Army, and when he did, he focused on the camaraderie of his unit rather than his technical achievements. The modification that bore his name in the unofficial communications of maintenance personnel became just another piece of military equipment history, its origins forgotten by everyone except those who had been there. The broader story of the 758th Tank Battalion followed a similar trajectory. They were recognized for their combat service, receiving a unit commendation for their performance during the European campaign. But the specific contributions of individual soldiers, the innovations and improvisations that kept the unit effective, were largely lost to history. The official records noted that the battalion had performed its duties satisfactorily. They did not note that the battalion had revolutionized Sherman tank maintenance procedures through practical engineering that defied conventional military bureaucracy. There is a particular irony in this story that extends beyond the usual ironies of war. The American armored forces in Europe succeeded in part because of their overwhelming material superiority. American factories produced tanks in quantities that the opposing forces could not match. But that material superiority would have been meaningless if those tanks had been unable to reach the battlefield due to mechanical failures. The modification that kept them running came not from the industrial military complex that produced the tanks, but from a mechanic in a segregated unit who understood that sometimes the best engineering is the kind that solves immediate problems with available materials. The Sherman tank itself had a complicated reputation. It was outgunned by heavier opposing vehicles. Its armor was vulnerable to advanced weapons, but it had one overwhelming advantage. There were thousands of them, and they could be produced faster than they could be destroyed. Morgan's modification enhanced this advantage by ensuring that more of those thousands actually made it into combat rather than sitting disabled behind the lines. This reliability became a form of psychological warfare. Opposing forces learned that destroying American tanks was often futile because more would simply appear the next day. The logistical and industrial superiority that the modification helped maintain created a sense of inevitability that undermined morale more effectively than any tactical defeat. The wire coil modification remained in use through the end of the war in Europe. Some tanks carried the original telephone wire coils that Morgan's team had fabricated in June 1944. Others had the refined spring steel versions produced by engineering depots. All of them benefited from a principle that Morgan had understood intuitively, that sometimes the most sophisticated solution is the one that can be implemented immediately with materials at hand. In the decades after the war, military historians would write extensively about American armored doctrine, about the development of the Sherman tank, about the challenges of fighting in the hedgerows of Normandy. Most of these histories made no mention of Morgan or his modification. It was a small detail, a technical footnote, the kind of practical engineering that happened constantly during the war, but rarely made it into the grand narratives of campaigns and strategies. But for the tankers who served in units equipped with the Morgan coil, it was anything but a footnote. It was the difference between spending the war fighting or spending it waiting for repairs. It was the knowledge that someone had cared enough about their survival to solve a problem that was killing them through mechanical attrition. It was proof that innovation could come from unexpected sources if given the opportunity. The men of the 758th Tank Battalion knew this. They knew that Curtis Morgan had saved their unit's combat effectiveness through simple ingenuity and practical engineering. They knew that his solution had been adopted across multiple divisions, improving the effectiveness of American armor throughout the theater. They knew that his contribution was significant, even if the official records would never fully acknowledge it. After Morgan's death in 1983, his family found among his papers a single technical diagram, hand-drawn on a piece of paper that had yellowed with age. It showed a wire coil mounted between a final drive housing and a hull plate, with careful annotations about compression ratios and stress distribution. At the bottom, in Morgan's neat handwriting, was a single line: "Sometimes the best solution is the one you can build today." That diagram represented more than just a mechanical innovation. It represented the kind of practical wisdom that came from understanding both the theoretical principles of engineering and the immediate demands of operational necessity. It represented the contributions of soldiers who served in segregated units, but whose innovations benefited the entire force. It represented the gap between official recognition and actual impact, a gap that characterized much of the African-American military experience during World War II. The wire coil modification was eventually superseded by improved designs in the final drive housings themselves, changes that were incorporated into later production runs of the Sherman and its successor vehicles. But during the critical months of 1944 and 1945, when American forces were pushing across France and into Germany, Morgan's improvised solution kept thousands of tanks operational that would otherwise have been deadlined waiting for repairs. The tactical implications were significant. Commanders could plan operations knowing that mechanical attrition would not cripple their armored forces before they even reached the objective. Infantry units could count on armor support arriving when promised, rather than being delayed by maintenance issues. The entire tempo of operations increased because tanks were spending more time fighting and less time being repaired. But perhaps the most significant impact was one that nobody planned and few recognized at the time. The success of Morgan's modification demonstrated that innovation in the military did not flow solely from the top down, from engineering schools and research laboratories. It could also flow from the bottom up, from mechanics and technicians who understood equipment at the most intimate level and who were empowered to solve problems creatively. This lesson was mostly lost in the immediate post-war period. The military, like much of American society, returned to pre-war patterns of segregation and hierarchy. The contributions of black soldiers were acknowledged in general terms, but rarely examined in detail. The innovations and improvisations that had emerged from segregated units were either forgotten or credited to the military system as a whole, rather than to specific individuals. It would take decades for a fuller accounting of these contributions to emerge, for historians to begin asking questions about whose innovations had shaped the war effort and whose stories had been left out of the official narratives. By that time, many of the men who could have provided first-hand accounts had passed away, taking their memories with them. Curtis Morgan was one of these men. He lived a long life after the war, raised a family, worked steadily in the automotive industry, and died peacefully in his sleep at the age of 66. His obituary in the Detroit Free Press mentioned his military service in one sentence, noting that he had served in an armored unit during World War II. It made no mention of the wire coil modification, of the thousands of tanks that had benefited from his ingenuity, or of the tactical advantages that his practical engineering had provided to American forces in Europe. The story of the Morgan coil survives now primarily in the memories of veterans and the research of specialized military historians. It is not taught in engineering schools as an example of field innovation. It does not appear in most histories of American armor development. It remains what it was during the war itself, a practical solution to an immediate problem, implemented by people who understood that sometimes you cannot wait for the perfect answer, when a good enough answer will save lives today. For the men who served with Curtis Morgan in the 758th Tank Battalion, his contribution was never forgotten. They knew what he had accomplished. They had seen it work. They had benefited from it directly. In the decades after the war, when they gathered for reunions, they would talk about the wire coil modification, about how Morgan had figured it out, about how it had kept their tanks running when other units were breaking down. These stories were told in VFW halls and at kitchen tables, passed down to children and grandchildren, who often didn't fully understand the technical details, but grasped the essential message, that their father or grandfather had served with someone who had made a real difference through practical intelligence and hard work. These oral histories kept the story alive even as it faded from official records. In the end, The story of Curtis Morgan and his wire coil modification is a story about the nature of innovation in wartime. It is about the gap between theoretical engineering and practical problem-solving. It is about the contributions of soldiers who served in segregated units but whose innovations benefited everyone. It is about how history gets recorded and what gets remembered. Most of all, it is a reminder that the great machines of war, the tanks and planes and ships that dominate historical accounts, were only as effective as the men who maintained them. Behind every successful operation was an army of mechanics and technicians who kept the equipment running, who improvised solutions when the manual didn't have the answer, who understood that reliability was as important as firepower. Curtis Morgan was one of these men. His wire coil modifications saved tanks, enabled operations, and improved American armored effectiveness during a critical period of the war. It was not a grand gesture or a dramatic innovation. It was simply good engineering applied to an immediate problem. But that good engineering, multiplied across thousands of tanks and hundreds of operations, had an impact that resonated far beyond its humble origins in a maintenance area in Normandy. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.